Hi, I'm Phil Norval, and this short video is about heat recovery for small businesses. I'm going to explain where heat recovery might be possible and the kind of benefits it may have in terms of cost savings and reducing carbon emissions. Because no process is 100% efficient, wherever energy is used, some of it is converted to heat and escapes into the environment. Even when a process requires heat, it can't all be contained perfectly, so there is always some level of waste. Historically, energy from fossil fuels has been so cheap that this wasted heat was not worth worrying about. Some processes, such as refrigeration or electricity generation, actually need heat to be rejected from them to operate correctly, so this kind of waste heat has generally just been accepted as a cost of operations. It's only been relatively recently, as fossil fuel prices have increased and there's been a growing need to reduce carbon emissions, that waste heat has been something worth taking seriously. In some situations, instead of wasting this energy, it's possible to capture some of it to use again, either by returning it to an earlier stage of the process or sending it elsewhere to serve a completely separate purpose. This is what we call heat recovery. Wherever there is a nearby need for heat, as much of it as possible should be brought from the waste source to where there is demand. This avoids using additional energy to deliver the heat requirement through more typical means, resulting in an overall energy saving. To see if there is potential for heat recovery within a business, a site-wide assessment should be made to identify all the major heat inputs and outputs. This means finding where heat is needed and where it is escaping. To give you a few ideas of what heat recovery looks like and where opportunities might be found, let's take a quick look at a few examples. One use of heat recovery that's familiar to a lot of people is actually found in their home's gas boiler. Most modern boilers are of the condensing type, which means that the steam produced when gas is burned is made to condense within the boiler rather than being allowed to escape from the flue pipe. The heat that's given off as this steam condenses is then captured through a heat exchanger and transferred into the heating system. Capturing the heat that would otherwise escape as steam can improve boiler efficiency by around 10 to 12%. It's common practice to try and minimise heat loss from a building by eliminating drafts as much as possible. In large commercial buildings, however, this airtightness means that some form of powered ventilation is then needed to ensure enough fresh air is supplied to maintain good air quality. In large buildings, this is usually done with an air handling unit, which combines balanced flows of extraction and fresh air ventilation, as well as potentially heating and/or cooling of the incoming air. To stop energy being wasted when heated air leaves the building via the ventilation system, there are a number of ways to transfer the heat from the outgoing air to the incoming air so that the heat is retained within the building without limiting the air quality. This can be done with a fixed plate heat exchanger, which passes one airstream over the other with a thin-walled barrier in between them to keep the two airstreams separate. Alternatively, a rotating thermal wheel can be used. This continuously absorbs heat on the areas that are passing through the extract air and then releases the heat as that part of the wheel passes through the colder incoming air. This can be very efficient, but it does result in some mixing of the two airstreams, which could be undesirable in cases where it's important to maintain air purity. If the supply and extract airflows are not running alongside each other, water can be used as an intermediary for transferring the heat. This system of pipes and heat exchangers that do this is often called a runaround coil. This can be more convenient, but it's generally less efficient than the other two options. Air handling units are usually specified and installed when the building is first constructed, and retrofitting this kind of system is not often feasible due to the cost and complexity of the installation work. Rather than using an air handling unit for the whole building, several simpler heat recovery ventilation systems may be more straightforward to retrofit. And these can be small enough to fit in ceiling voids or roof spaces, but serve much the same purpose as the larger air handlers, including having a fixed plate heat exchanger to retain the thermal energy within the building. These kind of units, although simple, can be expected to recover about up to 80% of the heat that would otherwise be vented from the building. Cooling is a very common process that's used in almost every industry, whether that's to keep food fresh, to stop staff from overheating, or as part of an industrial process. Regardless of the reason, it's usually done using a refrigerant system, which comprises a heat exchanger to absorb heat, called the evaporator, a compressor, and then another heat exchanger where the heat is rejected, called the condenser. It's the heat rejection at the condenser that's responsible for the warmth felt at the back of a fridge or freezer, for example. So it's therefore at the condenser that some heat might be recovered. This can be done directly by sending the warmed air to where it can be used for things like space heating. Alternatively, it can be done by rejecting the heat to water, which is used as a medium for storing recovered heat for use at another time, or for transporting the recovered heat to a different location. Industrial ovens and dryers can consume enormous amounts of heat energy and often waste a great deal of it as well. To remove fumes from combustion or from the materials being heated, as well as to remove moisture that's evaporated, there is usually some kind of flue or extraction system involved. Due to the high temperatures involved and the high flow rate required through the extraction system, large quantities of heat are often allowed to escape into the outdoor air. It's increasingly common, though, for these facilities to have some kind of heat recovery, because the heat is often of a high temperature and it's channeled into a single duct normally, rather than being emitted at multiple locations around the plant. This resource can be used in the same ways as other low-grade heat, i.e. for space heating and hot water, but occasionally the temperatures might be high enough to create steam for industrial heating or to generate electricity. Where temperatures are high enough and there is a large enough quantity of waste heat available, electricity generation might be feasible. The high cost of electricity could make this a very attractive option, but it's likely to have a very high upfront cost that needs to be paid back by a consistent and reliable source of waste heat. Normally, electricity is generated from a heat source by creating high temperature, superheated steam at over 400 degrees Celsius. Waste heat is rarely available at this kind of temperature, meaning a different technology is required. This is most commonly the organic Rankine cycle, or ORC, which works in basically the same way as a steam turbine generator, but rather than using water or steam, it uses an organic fluid with a lower boiling point than water. In this kind of generator, only a fraction of the heat going into the generator is converted to electricity, which means that most of the original wasted heat still goes unused and may be even harder to recover. That means that before choosing to install a waste heat electricity generation system, it's essential to compare the benefit of converting a small percentage of heat to electricity with recovering a much higher percentage, but for a lower value purpose, such as hot water for cleaning, for example. Another very common cause of waste heat in industry is from air compressors. These are found all over the place in most factories and workshops, as they provide a very versatile form of mechanical power. They are, however, quite energy inefficient. Typically, they only convert around 10 to 12% of the electricity used to power them into actually compressing the air, with the remaining 88 to 90% being wasted as heat. Compressors often use oil both to lubricate the system and to draw excess heat away, which is then fed through a radiator or heat exchanger to allow the heat to escape. It's therefore quite straightforward to replace this heat exchanger with an oil to water version, so that again the waste heat can be stored and piped to where it's useful. As we've seen, most waste heat is considered low grade, meaning it's at a temperature below the boiling point of water, and so it can't be used to either create steam or to generate useful amounts of electricity. This kind of heat on its own is therefore only suitable for things like space heating, domestic hot water, cleaning and drying processes. Low-grade heat can, however, be used to preheat something that needs to be brought to a higher temperature, making a contribution towards that heating process. For example, feeding waste heat into a boiler's return pipe would reduce the temperature increase that the boiler has to achieve. Alternatively, if waste heat's only available at a low temperature of around 20 or 30 degrees, but there is a very large volume of it being produced, its temperature could be upgraded via a heat pump to the point where it can serve a useful purpose. The heat pump option is a lot less straightforward to design and implement than a simple heat exchanger system though, so a heat pump engineer with specialist knowledge of these kind of scenarios must be consulted to ensure that an effective system is designed. It should perhaps go without saying that modifying any system that involves high temperatures should not be carried out without properly understanding the system and assessing the health and safety risks involved. A suitably qualified engineer should be appointed to design a complete system that will integrate with the existing equipment without any adverse effects on its operation or the site's health and safety. Wherever heated water is stored at temperatures of around 20 to 40 degrees C, there is an increased risk of harbouring or proliferating legionella bacteria. These systems must therefore have controls in place to reduce any of these bacteria to safe levels. Most often this comprises an electric heater and a mixing pump to raise the water to a sufficiently high and uniform temperature. Alternatively, if this water cannot be increased in temperature, then a biocide can be used to serve the same purpose. So I hope you found this video useful. You can find more information about heat recovery by downloading our fact sheet, or if you're interested in any other energy saving technologies, we have several more videos available. But thanks very much for watching.